Okay, so get that out. I think we copied it down, but I don't think we actually accomplished it. Looking at...
I got that.
I remember.
Yeah, 226.
Okay, so let's take a look at it at least.
I got Abraham Lincoln.
All right, so if we're looking at this problem, we want to find this measure right here. We want to find this arc measure right here. Okay, so let's talk about how we would find this arc measure right here. Well, what do we remember? We have all our nice theorems from Friday. So what are we going to do first?
Yes.
So what are we going to do first? What? Okay, we need to find what? MQN. So we need to figure out this. It would be really nice to know this angle right here, this theta, right? Okay, see that? Can we figure out that theta right there?
Yes.
How can we figure out that theta? They're supplementary, right? So if I take 180 degrees and I subtract 79, what is that angle theta right there, guys?
101.
What is it?
101.
So 101. Now, once we know that angle is 101, how does that help us? How does that help us? What do you think, Tanner? Well, it's not the same measure because remember, it's not a central angle, right? So where are the secants crossing? Inside or outside? Inside. When the secants cross on the inside, I believe we're going to use this formula, right? If I remember right, when the secants cross on the inside, we're going to use that formula right there, right? See that? So we're going to say it's 1/2 the sum of the two intercepted arcs. Okay. So going down here, we know that the measure of, now we know that theta is 101, right? So we know that 101 is equal to 1/2 of what? 86 plus x.
Right.
You guys understand that? So what we don't know here is one of the arcs. Okay? We know everything else. We know the angle. So now we're just going to use algebra. Now the first thing I would do is I'd multiply both sides by 2 to get rid of the 1/2. You guys see that? So solving this thing, I would multiply both sides by 2. And then that 2 is going to cancel that 1/2. And then I think 101 times 2 is 202. Am I right with my math there? Equals 86 plus x. And then we're just simply going to subtract an 86 from both sides. And then what does x equal, class? Do the math. What does it equal? What? What's 202 minus 86?
116.
116. Very good. And so we get x equals 116 degrees. And so now we know that this angle right here is 116. Now, there may be other ways to do this problem. I'm not sure. Maybe there is. A lot of these problems you can go in different directions and you can use different theorems and things like that. Okay, sound good? Now, if I was being a real engaging teacher, I would have you guys get out of, here's what, I'm just going to pretend that we're doing an engaging activity. Okay, so let's just pretend. You don't have to write this down. Okay, so here's the deal. What I would have you do if I had time, which I'm starting to run out of time, so I'm starting to just kind of spoon feed you a little more. And that happens sometimes. Sometimes you just don't have enough time to do an engaging activity and a discovery activity every single time. But if I was going to do a discovery activity, I would have you guys all make a circle for me. Okay? You guys understand that? And the next thing I'd have you do is I would have you do secant lines. Okay? Now, with the secant lines, I would have you just cross them randomly inside. So there's one secant line, and then here is another secant line. Okay, randomly crossing secant lines. Okay, guys got that? Now, what I would do is, okay, I would say this. So today we're not going to look at angles as much as we're going to look at sides, okay? And I'd have you measure this angle, this side length, sorry, not angle, but let's just call this, let's call this A, B, C, D, and O. Okay, so if I was being an engaging teacher right now, I'd have you create this. And then I'd have you, probably in millimeters, I'd have you measure these. I'd have you measure AO. I'd have you measure the measure of AO. I'd have you measure OC. I'd have you measure BO. And I'd have you measure DO. Okay? So probably just to keep this, let's just keep this consistent, we'll say CO. You guys understand that? So we got AO, CO, BO, and DO. Got it? All right. If you have BO, you should use DO, right? Okay. All right. Now, just kidding. That's kind of a joke. Okay. Now, and then I would say, okay, is there any relationship here? Now, the first thing I would say is I'd ask the class, do the secants bisect each other? And the answer to that is no. They do not bisect each other. Okay. So we cannot say that BO is always going to equal DO. And we cannot say that AO is going to equal CO. You guys see that? So that would be my first kind of question. Do they bisect each other? And most likely, if we all did random circles, not all of us would see that we wouldn't get equal segments here. You guys understand that? But there is a relationship here. And the relationship you would discover, and I'd probably have to point you in the right direction, is this relationship. So copy that down. Okay? All right. So, yep. And guys, I'm just going to warn you right now, I'm going to be feeding you a lot of theorems. Okay? So it's the nature of the game. It's just a timing thing. And so, yeah, I'm going to be feeding you a lot of theorems, so you're going to be writing these down. Okay, so here we go. It says if two chords intersect inside the circle, then the products of their lengths of the segments of the chords are equal. So it's not saying that they bisect each other. It's saying when you multiply the segments, they equal each other. In other words, they're proportional. So this is not kind of an obvious one, okay? But it actually becomes a nice relationship where we can solve problems. All right? So if you notice, A to E times E to B is equal to C to E times E to D. So it's a proportional relationship here. Now, you're probably like, who cares? But anytime we can write an equation, what we can do is find missing parts, okay? So we're definitely liking this because we can find missing parts. All right. So today we're just in kind of a little bit of a routine where we're going to be doing probably the next day or two is a lot of theorem copying and doing examples. I will try to do some application of this. It's very applicable. Anytime you're dealing in circles, okay, you're applicable. There's just so many different possibilities here. But right now, we just got to get this into our brains. Okay, so I think I have an example. Oh, no, what I did is just, okay, here's the next one. Now, again, if you don't need to write the words, that's fine. If you're a verbal person and you like words, that's fine also. So if it were me, I would draw the picture and the equation, then that's all I need. But If you need the words, great. It's up to you. So here's the deal. If two secants intersect in the exterior of the circle, so the secants now are intersecting outside the circle, then the product of the lengths of one secant segment and its external segment equals the product of the length of the other secant segment and its external length segment. Okay, so that's a little confusing. We'll talk about that in a second. Okay, so I'm going to give you a minute or two to write this down into your notes, and then we'll kind of see what's kind of going on here. Okay, again, if it were me, I would just copy down the picture and the equation, and I wouldn't worry too much about the wording. Okay. So what is this saying? It's saying that if you take AE, so AE is this entire secant segment from the circle all the way to the point of the intersection. Okay, if you take that measure, whatever that number is, and you multiply it times the exterior portion of that secant, which in that case is this guy right here, B to E, if you multiply these two things together, that's going to be equal to taking the entire secant here from C to E and multiplying it times its external portion of the secant right here. So I don't know if these colors are helping you or not, but it's just blue times green equals blue times green. You guys see that? That's all it is. And again, what's going to happen is, just classic geometry problems, is you're going to find missing parts of the secants, okay, using these proportional reasoning. All right? Okay, so it looks like I do have some examples here. Okay, so I want you guys to copy those down. And let me just get rid of this one really quick. Yes, I may scroll. Yeah, let me. You guys want me to scroll up? How about that? Is that good? So let's do this. Let's just do. It shouldn't be example 5. I just snipped it out. Don't do this one yet. So let's go ahead and do that one right there. We'll call this I'll call this example 1 today. Okay. All right. So here we go. There's example 1. So our job is to find the length of the, in this case, y. Okay. All right, Mr. Sam. No, Tanner, put an asterisk next to Tanner, please. Tanner's getting some extra stick time today.
Dude, just let me spin my wheel. I just want to spin my wheel.
We're just kind of getting some extra. So here's what's
Let me
been
spin my
happening.
wheel.
Don't worry, Sam. We'll get there. What's been happening with the sticks is that I have had a couple students come to me and say, hey, when I got my stick time, it was just, I didn't feel like I really got it. I only got like 2-3 stick pulls. And then so that way we're just kind of.
But Tanner's not even on the list.
He's not?
No. First time before you made the list.
Oh, okay. So Tanner, all right. So Tanner is getting extra stick time.
All right,
today.
well, then I'm removing him from the wheel.
Okay. All right. So Mr. Tanner, pull me a stick, and this student's going to start us off. All right, Mr. Wyatt. So we're actually going to be using not this theorem. We're going to be using this theorem, correct, Wyatt? Okay, so Wyatt, what's the equation we're going to write?
We are going to write GH. I don't know. Hey.
Okay, so I agree with. So I think, yeah. So GH times what? Times what?
HF.
Times HF is equal to what? It's equal to what, Wyatt?
DH.
Okay.
Times HE.
Times HE. Okay.
Oh, I get it.
I coded. Now,
Cody, what's your favorite color?
guys, we're going to go ahead and just we're going to go ahead. Cody, just catch up on the notes. Let's do this. Can everyone go to your pre-chosen assigned seats?
Yeah, why?
I don't want you guys continually moving. Everyone, no, Cody, that was not, what was your assigned seat, Cody? Right here. Okay. I want you guys to go to your we're gotten a lot of like musical chairs lately. No, I want everyone in their pre-chosen assigned seat. I'm sorry. Okay. So we are going to our original pre-chosen assigned seats. Nope. Nope. Okay. Okay. Here's the deal. So guys, we're getting a little, hey, I want to go sit next to my buddy because he's, we're not going to rearrange every time. We're going to finish out this class in these seats. You chose them. You're not moving. If your best buddy's not there, you're going to have to just sit alone for the day. I'm sorry. Okay, so Wyatt, go ahead and tell us what numbers to put in here.
Y times 2
equals what?
Equals 3 times 4.
Right. So it's a very simple thing. So this is just going to give me 2y equals 12. And so what does y equal, Wyatt?
I equals 4. 6.
Okay, awesome. So I don't think we need to do the next example because it's such a simple deal. I think we got it. Okay, so now what I want you guys to do is now we're going to use the external, what did they call this? They called it the secant product theorem. Okay, so you don't need your computer, Cody. We're taking notes.
I just can't see the screen when I'm sitting down. My eyes
What?
Okay, all right.
Yeah, I can't see it from back there.
Glasses don't make sense.
All right. So your job, ladies and gentlemen, is to see if you can't apply this theorem to these two problems. Go ahead and do that. Call this example number 2. And then I think we're going to try to do both of these. Okay, let's do it. Cody, do you need to sit further to the front?
Yeah.
Okay, so let's make your permanent assigned seat in front of, let's just go in front of Austin up there. But you're not moving around though, that's it. Got it.
You can see 5.
No, I can't.
Get some gloves.
I'm working on it.
Yeah, I think we should have a C5.
Okay, so in a minute here, I'm going to have Tanner pull some sticks here. And then we're going to go ahead and take a look at these. Okay, so Mr. Tanner, in a minute, we're going to pull a stick, and this student is going to take us through example number 2 using the theorem that we just developed, right?
I don't know if I did this right.
Okay, Mr. Tanner, who's the stick going to be?
Yeah, no, I did not do this
Who?
right.
All right, Austin.
I'm helping Cody get his theorems in since he was going.
So Austin, he can work with us. He'll get it. Okay. All right. So Austin, what do you want to solve for x, right? So we need to use this theorem right here, correct?
Yeah.
So we're remember what this theorem says. You take the entire secant and multiply it by its exterior portion, and that's equal to this entire secant times its exterior portion.
Yeah.
So when we do that, how are we going to set this thing up?
5x times.
Okay, so you're saying that you're using this entire secant right here. Is that right?
Yeah.
So how can we express that? I don't think that's 5x.
5 plus x
So that's 5 plus x, very good,
times 5.
times 5 equals what?
12.
12 times what?
6.
Times 6. Okay, so in this problem, ladies and gentlemen, we're going to have to use the distributive property. You guys see that?
Yeah.
Now, we could divide both sides by 5 right off the bat. It doesn't matter. But I'm going to use the distributive property here. So, Austin, when we use the distributive property, what do I?
25 plus 5
Equals what?
72.
Okay. Keep going, Austin.
Then you subtract 25,
So we're gonna subtract 25 from both sides.
which is 47.
So we get 5x equals what?
47.
47. What's next?
Divided by 5.
Divided by 5.
X equals 9.4.
9.4. You guys agree with that?
Yeah.
Okay.
Good job.
Excellent job, Austin. Well done. Okay. Example number 3. I want the next example number 3 is let's go with Cody. I mean, no.
You meant Will, I think.
Tanner, pull me a stick. Martin. All right, Martin. What would be the equation you write for example number 3, Martin?
10 plus y
So we have 10 plus y. Keep going.
times 10
Times 10 is equal to what?
27
27 times what? What's the external part, Martin?
He said 9.
9. Okay, good. All right, Tanner, pull me another stick. This person's going to finish it for me. George. All right, Mr. George, finish this off for us.
Well, we multiply 27 times 9.
What is that, George?
Well, let me see.
Yeah, go ahead and take that.
Okay, thank you.
I bet it's 243.
Oh, yes. Thank you, Austin.
243?
Welcome.
Do you agree with that number, George?
Yep.
Okay, keep going, George.
And then we'd use the distributive property on the other side.
Yep.
And that'd be 100 plus 10y.
Okay, keep going.
Well, at this point, we'd subtract 100 from both sides.
Perfect.
And
Yep.
that'd be 143 on the right side.
So 10y equals 143.
Yes, sir.
Okay, George, finish it off.
We'd isolate y by dividing both sides by 10.
Very good. And so what's y equal to, George?
14.3.
You guys all agree with 14.3?
Yeah.
Okay. This stuff is pretty simple, right? You just got to remember it. Okay. It's pretty simple stuff. You just got to remember it. Okay. Now I want you guys to do a little more funsy problem. So now let's try this one together here. So get this copied down. I really like a problem like this for the test. I like a problem where it's going to involve a little more complex algebra.
Will most of them though be like the questions earlier?
Some will. You got to think of this. This is like this problem like this is going to be like a little more like a high. Okay, so we're going to do this one together. We're just going to set this one up. I'm going to give you guys a second to copy it, and then we're going to do this one together. Okay, and I think we're going to get some really good stuff here. Yes?
So you know that algebra test we have to take for Doherty?
I haven't heard from Doherty. Yeah.
Well, but what if we do terrible on it?
Then they have to make a decision whether you need to retake algebra. They have before. Yep. So
Is there like a high percentage of passing people?
usually from geometry, there's a high percentage, yes. But I have not heard from Doherty yet, so we'll see.
Let's hope we don't.
Okay. All right. I did mention it to Mr. Sansoni and Peterson, and they said they haven't heard because their algebra kids have to take the test also. All right. So remember, we're going to use that same theorem we just used here. I really like this problem. Okay. So Tanner, pull me a stick. Now, all this student is going to do is help me set it up. Xavier. Okay, Xavier, help me set this problem up. X plus 4 plus x minus 2 times x minus 2 equals what? Equals 9 times what? 4. Okay, does everyone see that? Now, the next step we need to do is we need to simplify inside of this expression right here. Okay? Tanner, good job, Xavier. Pull me a stick, Tanner.
Not here.
Okay, so Dakota, your job is to simplify this blue portion of this. So what do you got?
I got 2x minus 2.
2x minus 2, very good, times x minus 2 equals, and then help me out, what's 9 times 4? 36. Very good. Okay, now, here's...
It would be 2x plus 2.
Yeah, it's
Oh, yeah, it would.
You're right.
I'm so big.
Okay, good. Now we're getting into some good algebra right here, okay? Now, stop and listen. This, if Doherty comes, this problem is going to be a very, a common problem, okay? So watch the algebra here. So I hear FOIL, I like that. So Tanner, pull me a stick. This student's going to FOIL it out for me. All right, Mr. Brady. So we're going to FOIL this out. You remember your FOIL skills, Brady?
I believe so.
Okay, let's do it. Here we go.
All right, so first, it's going to be 2x times x.
What's 2x times x?
2x squared.
2x squared, good.
Okay, and then outer, which is 2x times negative 2, which is negative 4x.
Negative 4x, good.
Then we have inner, which is 2x.
Plus 2x, yep.
And then last, which is negative 4.
Negative 4, good. All right, one more step, Brady. I want you to simplify this for me. So combine your like terms.
Negative 4x plus 2x is negative 2x.
So this is going to be 2x squared minus 2x minus 4 equals 36. Do you agree with that?
Yep.
Okay. Now, ladies and gentlemen, we have something called a quadratic formula here. A quadratic equation. Okay? We have a quadratic equation here. So, when you solve a quadratic equation, I don't really want to moan about it. I just want to show you this, okay? So, when you solve a quadratic equation, you've got to set it equal to 0. How do I know it's a quadratic equation? Because it's got a degree of 2. Its highest power is 2. You cannot just solve this by trying to do a square root on both sides. You can't do that because you've got x's. So the first thing we're going to do is we're going to subtract 36 from both sides. Okay, we're going to 0 it. Okay, when we do that, we get 2x squared minus 2x, and then when we subtract negative 4 minus 36, I believe is minus 40, right? Equals 0. Okay. Now, here's the thing. Let me just copy this really quick. Give me a second here. I'm going to copy this, and I'm just going to take it down to a place where I can. Now, you could just do the quadratic formula, but I think we can do it a little easier way. Now, here's the deal. When you always want to use something, and I want you to write this down, called the zero product property rule. Okay? The zero product property rule. Well, I'm teaching. Okay, now, what does the zero product property rule say? It says if you have something A and you multiply it times something B and you equal 0, what can you guys tell me about A and B? Either A equals 0 or B equals 0. So if we could rewrite this equation as A times B, then we could set each one of the factors equal to 0 and solve for x. You guys see that? Okay. So what we're going to do now is Now, I'm noticing this 2 in front of the x squared. I hear quadratic formula. But yeah, the quadratic formula, but the problem is sometimes the quadratic formula can be a little tedious, and I am a much bigger proponent of factoring. But factoring with a coefficient of other than 1 in front of x squared can get a little tricky, but I'm noticing I can factor out a greatest common factor of 2. You guys see that? So when I factor a 2 out here, I get x squared minus x minus 10 equals 0. Now, minus 20 equals 0. Sorry. Now, it may factor, it may not. Okay, so let's see. It may factor, it may not. Well, let's see here. If we try to factor this thing, we know we're going to get x and x. We have to, right? We know we're going to get a negative and a positive. Does everyone understand why? Because the 20 is negative. The product is negative. The only way to get a negative product is 2 different signs. So we know we have a plus and a minus. So here's the thing. We're going to look at the factors of negative 20 that add up to negative 1. Can anyone think about that? What are the factors of negative 20 that add up to negative 1? Think about the factors of 20. There's 20 times 1. There's 10 times 2. There's 5 times 4. Do any of those add up to negative 1? Okay, so I'm hearing 5 and 4. 4 minus 5 is negative 1. So the 4 is going to be the positive, and the 5 is going to be the negative. Do you guys see that? Now, you want to make sure you bring down your GCF just because you don't want to just lose it. Now we can use zero product property rule. We actually kind of have an A times a B times a C equals 0, right? Okay, so we can set 3 things equal to 0. We've factored it out, so we could set 2 equal to 0, which is never going to happen, so that can just cross out. Your 2 is never going to equal 0, so that's a meaningless factor, so you can just get rid of it. But you have x minus 5 equals 0, and you have x plus 4 equals 0. See that? Now we solve for x. Remember how we said that a equals 0 or b equals 0? Let's say this is c, this is a, and this is b. We have to set them all equal to 0. C is never going to equal 0 because it doesn't have a variable. So now we solve, and this one we're going to get, if you solve it in your head or whatever, this equals x equals 5, and this is x equals negative 4. Now, in an algebra class, you would just be done. But in a geometry class, we have to go back and see if these actually could be possible. Okay, so if I go back to the original equation and I figure out x, where's the original equation? Could x actually equal negative 4? No, because if you have negative 4 minus 2, you're getting negative 6. So that can't be a distance, right? That's crazy talk. So in geometry, our answers sometimes are meaningless. So negative 4 is not a possibility. But could positive 5 be a possibility? Absolutely. Positive 5 will not give us any negative values. So now we know that x equals positive 5. Y'all see that? Okay. Did that help with factoring a little bit? Okay. That's the kind of thing you're going to see on your Doherty test. Okay. If you get it. All right. So the last thing I want to do, and I can't believe I didn't copy and paste it, so I need to go back and get it really quick. So I need to go get this really quick. So let me do it here. So the last thing we need to get is this. Sorry. So this is where I get these problems from. Okay, this is the last thing we need to get. Okay, so we're going to deal with a tangent and a secant. So I'm going to copy and paste this into our notes. Okay. So now I want you guys to write this down. So notice, guys, now we have a secant and a tangent. So now, and it kind of makes sense why it would work. but your job is to copy that down. I'll read it, and then you guys can copy down what you need, and then we'll practice these. If a secant and a tangent intersect in the exterior of a circle, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. Okay? So we're going to start out just like we normally do with secants. We're going to look at the entire length from A to C, the blue length. I think I did that before. Blue. And then you're going to multiply that times this green portion right here, right? But the only difference is it's not going to, you don't have another secant to work with here. You have a tangent. So what you're going to do is you're just going to say tangent squared. So the tangent is going to be squared. So it's that red portion squared. Okay, see that? So you can think of it also as DC times DC if you wanted to. Okay? So get that into your notes. And then, so what do we have? Just to kind of make sure. So if you're a color, I'm a very visual person. So I could see, okay, I'm going to take the blue portion. I'll put it in parentheses. I'm going to take the blue portion, and I'm going to multiply it times the green portion of this problem. And then I'll put that back like this. And then that is going to equal the red portion times the red portion. So here's a way, I don't know if this is, you're seeing my brain in action here. I don't know if my brain is making sense to your brain. People think of things differently, but that needs to be red. So is that kind of helpful to see the colors? Does that kind of make sense? Not really?
Do you think
So,
you could do the color coding thing on the test?
Yeah.
I don't know. Okay, so blue times green equals red times red. What do you think, Nicole? Do you kind of think, do the colors help a little bit, maybe like that?
It helps, but like, I don't know, I guess not every problem's gonna have blue, green, and red, just dark red.
No, that's why you have to do this, right? Okay, so another minute here, and now let's go back and do a couple of examples here. Hopefully we get some good factoring in again. That was fun. That was really fun. Okay. All right. Here we go. So let's try these. Okay. So let's go ahead. If you didn't get that, maybe I'll get you a second. But again, there's no sense in copying down all the words. The equations and the pictures and the equations get the job done. Okay, so we want to find Z right here. Okay? So Tanner, pull me a stick. So we're going to write this out. So who you got, Tanner? Nicole? All right, Nicole. So what's the first thing we're going to do on this one right here? Nicole? So Nicole, I'll help you out. If we're doing colors, the first thing we need to do is find this in this whole blue length right here, right, Nicole? So how would we find that blue length? You'd add them, right? So what's that, Nicole? What?
14.
So we get 14. Okay. Equal. No, we got to multiply that, right? Now we need to multiply it times the green section right here, right, Nicole? So what's that? 6. Okay, we'll do that math here in a minute, Nicole. Now what we need to do is multiply. That's going to equal this red section right here squared, right? So what's that going to be? That's going to be Z squared. Now, this one, you will not need to factor it because you only have Z squared. You don't have a plus Z sum Z. You guys understand that? So when you only have one variable squared, it makes life a lot easier. So you guys help me out. Tanner, pull me a stick, and this student's going to multiply 14 times 6 for me. Who is it? Rachel. What's 14 times 6, Rachel? What? 84 equals Z squared. Now, bye, Nicole. What's the next step, Rachel? Stick with me on this. How are we going to solve for z, Rachel? You're going to square root both sides. Now, so z is going to equal plus or minus the square root of 84. Technically, in algebra it would be, but we're in geometry, so we can throw out the negative, right, guys? So we can, just to know that, hey, we got to do plus or minus, but negative distances are not meaningful in geometry. Now, there's a couple things we could do. We could stick it in the calculator, right? Or what I would like to do is see if there's a perfect square inside there. Let's reduce radical form this thing. That's a good. So, Tanner, pull me a stick. Who is it? Will. Okay, Will. Will, don't look surprised. Your stick is in there. You know, you're going to, it's just the way it goes. Okay. Now, Will, I know at least of one perfect square inside of 84. What's a perfect square that goes into 84, Will? I know one for sure.
4.
Okay, let him think. He's got a brain. Will. So remember your perfect squares, Will. Perfect square. We get 4, 9, 16, 25, 36, 49, 64, 81. I think we don't need. I know for sure 4 will go in there, right, Will?
Yeah.
Now, will 16 go in, guys?
I don't think so.
Yeah.
Will it? How many times?
Never mind.
No, 5.25.
Okay. I know 25 won't. I know 9 won't. Will 36 go into 84? No. So it looks like, Will, 4 is our only perfect square, right? I don't. What?
No, wait.
7 and 7. What?
Okay, now,
What?
so this is going to be the square root of 4 times, Will, what's 84 divided by 4? Will?
Okay.
21, right? So what's the square root of 4, Will? 2. So if we were doing it in reduced radical form, it would be 2 square roots of 21, and we'd be done. You guys see that? Or you could stick that in the calculator and get square root of 84 is going to be about 9 point something, right? Yep. Okay. Ladies and gentlemen, I did add some new delta math. It's due next Monday. So it's called, just the delta math is called Circles Homework Number 2. And delta math is saying that if I look at it, sorry, no one's done it yet. Delta math is saying that this assignment should take approximately 67 minutes. So you have 1 week to do 67 minutes worth of math problems. Mr. Roden signing out.